a dual, I'm doing this because if I put it on YouTube, I can only do it in 11-minute increments. If you have a dual circuit, it means that the voltages are replaced by currents, current sources are replaced by voltage sources, resistances by conductances, capacitors by inductors. So there's like these, they're considered dual elements, and because the math, if you do that replacement, the math is the same. Anyway, so whether you're doing node voltage analysis or mesh current analysis, this little thing works. Do like the Super Kaufman. So draw it, label it. So in this case, I'll be labeling node voltages. The third step has to do with dependent sources, and I'll show you, since we have a dependent source, I'll show you what you need to do with it. And then the fourth step has to do with if you have super nodes or super meshes, which unfortunately we do. We have a super, but we're not doing mesh current analysis, darn. Well, I'll do mesh current analysis in the second part. And then the last step has to do with Kirchhoff. And so if you're doing node voltage analysis, you're going to do Kirchhoff's current law. If you're doing mesh current analysis, you're going to apply Kirchhoff's voltage law to all of the, well, I'll get there. So these 5 steps, you remember it, do like the Super Kaufman. And why da instead of the? Anybody old enough to remember Willie Brown being the mayor of San Francisco? He was called Da Mayor. so it worked. Anyway, so I drew it. Okay, so that's step 1. Here it is drawn. It's got all of the things labeled. It looks great. Draw it neatly. 2, label the node voltages. Okay, so with node voltage analysis, we just pick a reference node. You know, I'm going to draw this over because I like to draw it using what's called like a linear graph, which means that you don't have these corners and you collapse nodes into one point. It's kind of easier, I think. So I'm going to do that. Noticed a mistake on my own words, and that's why I'm hesitating, but I guess I can get around it. Okay, so this is node A here, right? And this is node B. I'm going to label this C and this D. Okay, so if I want, you know, if I just arbitrarily, I think I've got it right. Check my work here. Does this look like this? Yeah. Okay, so I'm going to label the node voltages now. I'm going to choose B as my reference, which means that VB is 0. Right? If I'm choosing the node B as my reference node, I'm going to label this voltage here at B, VB, because it's node B, and it's equal to 0. I put the A like this because I envisioned later that I wanted to actually label the voltage at that node. So it's the node voltage VA. Sorry, this is getting a little bit squeezed in. Let me put this on VOC. Okay, so this is VD. Here, let me see if I can separate it from my, okay. And then this is node VC, and now I've labeled my node voltages. I've got the reference node, and then I've labeled all the other nodes. All right, so that's the second step. You know, I love keeping to-do lists and then crossing things off, so good. I've done that, check. So, for the dependent part, you know, that third step, something to do with the dependent source, here's what you have to do with it. You look at the controlling quantity of the dependent source, and you want to write that controlling quantity in terms of node voltages. Okay, because ultimately, and I forgot to ask this question, why do we want to use node voltage analysis or mesh current analysis? I mean, you know Kirchhoff's voltage laws and Kirchhoff's current laws. You could probably just solve the problem using those. So why go through this learning of these 5 steps?
More complicated circuits.
Yes, for more complicated circuits, for you to just kind of randomly say, okay, I'll maybe do Kirchhoff's current law here, Kirchhoff's voltage law here, and hopefully get enough equations and the right amount of unknowns and pray to the God of circuits that it all works out. This guarantees it. This guarantees a result. It guarantees that you will find n equations in n unknowns. And the unknowns, in this case, will be the node voltages. And if I can get the node voltage, I can get VOC, because notice that VOC is VA. So if I can get VA, then I'm halfway done with my problem. Okay, so that's why you want to learn node voltage analysis and mesh current analysis. Because when the test comes and you see this complicated circuit and you're being asked to do something, you don't have to panic. You just have to remember these steps and follow them faithfully. Now, it does take a little bit to learn the steps because you're going to get to that 3rd step and say dependent source. Oh my God, what was I supposed to do with it? You're supposed to look at the controlling quantity of that dependent source and write it in terms of node voltages. Of course, if we were doing mesh current analysis, you would want to write it in terms of mesh currents. Okay, so there's the controlling quantity. I'm on step 3. This is it in the circuit. Well, actually, let's look at this picture. Here it is. Can I write this current in terms of node voltages? Ooh, wait, there's something wrong here. Oh, you know something? I forgot an important step. When I label the node voltages, oh, never mind. Okay, sorry. I'm getting ahead of myself. I'm looking at this branch and I'm having trouble figuring out how I'm gonna write IX in terms of node voltages. But then when I see that IX is also in this branch, it's much easier to see how I can write it in terms of node voltages. So who can do that for me? It's going to be 0 minus VC over 2. What did you say? Why 16? The voltage across this resistor well, is 2. Okay, let me just make sure you understand. A node voltage means the voltage of this node relative to ground, relative to the reference node. So it's similar if I were going to draw this 2 ohm resistor here like this, and then this is VC, and then this is like this, and then this is VC, and then this is the reference. The current is going this way. So it's VB minus VC over 2 is equal to IX. So VB minus VC over 2. But VB is 0. So it's actually minus VC over 2. Okay, so does everybody see that Ix is minus Vc over 2. Everybody's okay with that? Okay, great. We're going to need this to plug into the n equations and the n unknowns that we get, because the only unknowns that we want in those equations are the node voltages. Vc is a node voltage, Ix isn't. So that's why this step is important, because we're going to be using this later. Okay. Super stands for, in this case, super node. So we have to identify all the super nodes, and then we need to write an equation that goes along with them. So, do we have any super nodes? So you have to know the definition of a super node. Anyone know it? It's any voltage source, and it could be a dependent voltage source. Any voltage source and the two nodes on either side. So we have a voltage source here. The two nodes on either side are here. Go ahead and actually draw kind of a big circle, dotted line. Not really a circle. Anyway. This thing here that I've just drawn